Hello everyone and welcome to our CIVL302 final project presentation, where we will be comparing two different septic systems, a traditional system and one that uses an aerobic treatment unit. Our group members are Osberto Beltran, Cameron Jameson, Mason Jones, myself, Chris Reclusado, and Matthew Tarr. The use and treatment of water is an ever-increasing concern to our modern society, especially in California, where the recent drought led to local governments to enforce water use limits for residents. The effects of the drought were felt across the region, both in cities and rural areas. As the drought worsened, some rural community members found themselves having to drill new and deeper wells to maintain a steady source of water for their property. Even with strong efforts to conserve water, many residents have found that their efforts weren't enough. This study will analyze the benefits of replacing the traditional septic system with an aerobic treatment unit to enable water reuse in a rural setting. An ATU utilizes the same basic concept employed by urban wastewater treatment plants. Using an ATU would bring the technology of a treatment plant to an individual rural properties that don't have access to sewer systems. The EPA estimates that the average American household uses 30% of their total water consumption outside for things such as watering lawns and gardens. Using a septic system with an integrated aerobic treatment unit would allow wastewater to be released at surface level for watering purposes, as opposed to disbursement through a leach field. The goal of our project is to compare the environmental and economic costs and benefits of these two types of septic systems. Our system boundary begins at the inlet to the tank system and ends at the outlet, whether that be a leach field or a drip irrigation system. To begin our comparison, we'll look at a traditional septic system. These systems typically use a single septic tank where an anaerobic process takes place to decompose organic matter in wastewater. These systems require a leach field to release the treated water back into the groundwater, where layers of soil and rock complete the filtration process before the water reaches the water table. The output from the septic tank is not safe for surface release and therefore cannot immediately be reused. Standard septic systems certainly have their benefits. They are simple to construct, and when used properly, maintenance is minimal. They can be set up to be gravity fed and therefore do not consume any energy during the operation phase. Aerobic treatment units are more complex. The process begins in a pre-treatment tank where an anaerobic process takes place to precondition the wastewater. It is then pumped into an aeration chamber where air pumps agitate the water to stimulate an aerobic decomposition process. The water is then moved to a final chamber of the system where chemical conditioning of the water takes place before it is released to the surface. The water that exits the system is safe to use for watering lawns and gardens. Utilizing this technology would enable rural residents to decrease their household water intake by using the treated water to meet their outdoor needs. To compare the economic and environmental viability and benefits of an ATU, we will perform a life cycle analysis for both systems. We began our analysis by assembling an inventory of system inputs and outputs relative to our system boundary. We defined our functional unit as 250 gallons of wastewater treated per day over a 20-year period. As you can see, we have included the inventory for the aerobic treatment unit as an example. Both systems are similar in their construction inputs. However, the ATU requires an additional tank and adds drip irrigation system to replace the traditional gravity trench. The ATU also requires an energy input to run the pumps. With our inventory and goals in mind, we focused on two principles of green engineering: prevention instead of treatment, and integration of local material flows. By reusing water on site, an ATU prevents further input of fresh water and utilizes a local material flow that would otherwise go to waste. In order to properly compare these systems, we used three key sustainability metrics. On the environmental side, we focused on water usage, carbon footprint, and eutrophication. On the economic side, we focused on operation and maintenance costs and a comparison of the net present worth of the two systems. Given these metrics, we chose to use the recipe European midpoint indicators to complete our life cycle analysis in CIMAPRO. We analyzed the potential for climate change, eutrophication, and water depletion. The results of our LCA showed that an aerobic treatment unit has a significantly greater impact on climate change than a traditional system, as a result of the added energy component. In order to counteract these effects, we decided to incorporate an ATU system that utilizes a solar energy mix. As you can see, this significantly lowers the climate change impact of an ATU to the point where it has a smaller impact than even a traditional system. For the eutrophication potential, we found the system with the ATU performs slightly better than the traditional septic system. This may be explained by the reduction of treated freshwater inputs. However, we found that the use of solar power adds to the eutrophication potential, making it the worst option for this category. In terms of water depletion, we found both aerobic systems have no potential for water depletion due to the avoided freshwater input. In fact, they have a negative water depletion score. On the other hand, the traditional system has a small potential for water depletion due to its material and construction inputs. Moving to economic analysis, we focused on the net present worth of the two systems. Shown here is an example of the cash flows associated with each system. This takes into account initial costs, annual operation and maintenance costs, as well as the annual benefits of avoided water usage. We also performed a sensitivity analysis on the ATU, taking into account the worst case scenarios while varying annual electricity costs, annual operation and maintenance costs, and the capital investment costs. This system is most sensitive to an increase in capital costs, followed by operation and maintenance, and lastly, electricity costs. To summarize our findings, in terms of climate change, the solar-powered ATU performs best, while the standard electricity ATU performs significantly worse. In terms of freshwater eutrophication, the standard ATU system performs best, while the solar-powered ATU performs significantly worse. In terms of water depletion, the standard electricity ATU performs best, though the solar-powered ATU performs at about the same level, and the non-ATU system performs significantly worse. Here you can see all the environmental impacts together. This shows that the climate change potential has the biggest impact overall, with the water depletion being the next largest. Using these three indicators, for sustainability reasons, we would recommend the use of the solar-powered ATU system. Despite the offset from the avoided water benefit, the aerobic treatment unit still costs significantly more than a standard system. In conclusion, the solar-powered ATU is best in terms of environmental impact, and the traditional septic system is about $6,000 cheaper than an ATU system. If you wish to save your wallet, go for a traditional septic system. If you wish to save the polar bears, go for a solar-powered ATU.